Hello, my name is Vladimir, and today I'm going to talk about audiovisual synchronization. Okay, what is audiovisual synchronization? It is the task of finding temporal alignment between audio and visual tracks. Let me illustrate this by an example. Now my talk is out of sync and the audio is slightly ahead of what you see. Let me fix it now. Now it should be better. We want to train a model to do it for us automatically, so if prior works were detecting if the video is in sync or not, we want to go further and train a model to find the exact temporal offset. What is interesting is that for open domain video, synchronization signal can be sparse in time and space at the same time, yet prior works were considering only dense synchronization signals. What do we mean by dense and sparse synchronization signals? For example, cropped talking head videos give you a dense synchronization signal in both time and space, and most of the prior works were considering this type of data. Synchronization of talking heads is pretty much solved nowadays, so instead, we're interested in synchronizing videos with sparse synchronization cues. Consider this video, which is both sparse in time and space, because synchronization cues occur rarely and rarely in time, and also the visual indication is very small in the frame. To solve this problem, we need a model that can process longer video clips to catch the sparse synchronization cues. And in this work, we will focus on this kind of videos. To develop a synchronization model for sparse videos, we need a dataset and architecture that handles longer video inputs. Since there is a lack of any dataset for this, we curated a new dataset called VGG Sound Sparse. It is a subset of VGG Sound dataset, which is a large-scale audiovisual dataset. We curated 12 data classes such as dog barking, chopping wood, bowling, and so on. We also proposed a novel multimodal transformer architecture that allows processing longer video clips. Given audio and visual streams that are potentially out of sync, we first extract features from them. Notice that the size of the features grows with things like frame rate or spatial resolution, which should be quite high to capture the synchronization cues. Inspired by perceiver and debtor, we suggest having a small set of trainable vectors, let's say 16 of them, that will query important information via cross-attention modules. This way we can process longer input sequences, and the audio features are processed in a similar way. Then we fit the refined queries to the transformer encoder that predicts the temporal offset between audio and visual streams. And in this work, we consider the discrete offset amounts and train the model as a classifier with a standard cross-entropy loss. Since most of the videos online are in sync, and we can actually artificially desynchronize them by some amount and try to predict it. We pick one of the 21 classes of offsets ranging from -2 seconds to +2 seconds with a step size of 0.2 seconds. Notice that if the video is in sync, the offset is 0 and it is one of the classes. Each video in the dataset is 10 seconds long, and we take 5-second audio and RGB streams that is offset by the selected amount. In our experiments, we found that pre-training on dense in-time videos helps during training with videos that have sparse signals. So we pre-train our model on the recorded stage talks like TED Talks, and then fine-tune it on the videos with sparse signals from VGG Sound sparse dataset that we introduced here. We compare our model to the baseline, which is the state-of-the-art architecture for audiovisual synchronization. We compared the models on both dense and sparse data settings and found that our approach is significantly better on both. We found that training on longer video clips helps to improve the results, as well as if the model is trained with more data like full VGG sound or audio set, it improves the performance further. Let's take a look at the few qualitative results. Alright, if you're interested in trying out the model yourself, we have a COLAB notebook and a code available on GitHub. Also take a look at the paper for more details. We found that common codecs leave temporal artifacts that can compromise training, which we haven't covered today. With this, I would like to conclude, and I wish you a great day.